how microfluidics and nanotechnology enable compact biomedical diagnostic systems. Big picture. What are microfluidics and lab on a chip? Microfluidics refers to the manipulation of fluids in channels with dimensions of tens to hundreds of micrometers. At this scale, we work with extremely small amounts of liquid, often too small to see with the naked eye. A lab-on-a-chip system integrates one or several laboratory functions on a single chip. Instead of using large laboratory equipment, processes like mixing, reacting, and detecting can all take place on a small device. The advantages include reduced sample volume, faster analysis, and high sensitivity. Because everything happens on a small scale, reactions can occur more quickly and require less material. Importantly, combining microfluidics with nanotechnology improves detection capability and supports further miniaturization. This combination makes these systems especially useful for biomedical diagnostics. Why microscale physics matters. To understand how these devices work, we need to understand fluid behavior at small scales. In microfluidic systems, laminar flow dominates. This means fluids move in smooth, orderly layers instead of turbulent mixing. The Reynolds number is typically much less than 1. At such a low Reynolds number, inertial forces are much smaller than viscous forces. Because of this, diffusion governs mixing in microchannels. Fluids do not mix through turbulence. Instead, molecules spread slowly by diffusion. Also, surface forces dominate over inertial forces. At the microscale, surface effects become more important than momentum. These physical conditions determine how microfluidic devices must be designed. How microfluidic devices are fabricated. The most widely used fabrication method is soft lithography using polydimethylsilicone or PDMS. In this process, PDMS is cast against a master mold. The mold is usually created using photolithography. After curing, the patterned PDMS is bonded to another surface to form sealed microchannels. Bonding methods for channel sealing are essential because the fluid must stay confined within the designed structures. PDMS has advantages such as optical transparency and biocompatibility, which are important for biological experiments and optical detection. However, it also has limitations, including solvent swelling and gas permeability. These strengths and limitations influence how devices can be used in practice. Beyond PDMS, other fabrication platforms. Although PDMS is widely used, it is not the only option. Other fabrication approaches include glass micromachining, silicon-based microfabrication, and thermoplastics produced by injection molding. This shows that non-PDMS platforms exist and highlights material diversity. Different materials provide different mechanical, chemical, and manufacturing properties which can affect device performance and large-scale production. Adding nanotechnology. Why it changes performance. Nanotechnology is integrated into microfluidic systems to improve sensing performance. Nanoparticles increase surface area. A larger surface area allows more interaction between the sensor surface and target molecules. Nanostructures improve signal transduction, meaning they help convert biomolecular interactions into measurable signals more efficiently. Functionalization enables biomolecular recognition. By modifying surfaces at the nanoscale, specific molecules can selectively bind to their targets. Overall, nanomaterials play an important role in increasing sensitivity. What is a microfluidic biosensor? A biosensor consists of a biorecognition element and a transducer. The biorecognition element interacts specifically with a biological target. The transducer converts that interaction into a measurable signal. In microfluidic systems, biosensors can use optical, electrochemical, and mechanical detection methods. Integration within microfluidics enables real-time analysis, meaning detection can occur continuously as the sample flows through the device. Detection mechanisms: optical and electrochemical. In optical biosensors, fluorescence-based detection is commonly used. Light emission indicates the presence of a target. Another optical method is surface plasmon resonance, or SPR. SPR allows detection of molecular interactions at a surface. It can be used in labeled or label-free approaches. In label-free detection, the interaction is measured directly without attaching a fluorescent or chemical tag. Electrochemical biosensors include amperometric, potentiometric, and impedance metric. These measure electrical signals that change when a biological interaction occurs. Nanomaterials improve electron transfer in these systems, which increases sensitivity. These approaches are suitable for miniaturization and work well with microfluidic integration. Biomedical applications. Microfluidic biosensors are used in disease diagnostics and pathogen detection. Because they require small sample volumes and allow rapid analysis, they are especially useful for point-of-care testing. Point-of-care testing means diagnostics can be performed near the patient instead in a central laboratory. This is important for faster decisions and better access to testing. Challenges and limitations. Despite their advantages, there are important challenges. Reproducibility issues can occur during fabrication and operation. Integration complexity increases when combining microfluidics, nanomaterials, and detection systems. There are also commercialization challenges. Moving from laboratory prototypes to widely available products is not simple. Future directions and takeaway. In the future, research focuses on improved integration and increased automation. There is also strong interest in personalized medicine, where diagnostics and treatments are adapted to individual patients. Microfluidics combined with nanotechnology offers a pathway towards compact, sensitive, and potentially accessible diagnostic systems. In summary, by understanding microscale physics, fabrication methods, sensing strategies, and current limitations, we can see both the strong potential and the real challenges of these technologies.